React is the most popular front-end framework in the world, and if you have ever wondered how to create one yourself, this video is for you. We're going to dive into how to implement a basic virtual DOM reconciliation algorithm and a basic hook for React components. Before we write our first line of code, let's go over a few fundamental React concepts like JS6. JS6 is simply synthetic sugar. Instead of writing a lot of unreadable code like this, we can use a more readable form. So you have a file with a JS6 extension, which Babel will take and transpile into pure JavaScript. That transpile file is then executed by the browser. So let's create our first element. We're going to put JS6 aside for a moment and do it in pure JavaScript. So what is an element in React? It's a representation of a DOM element inside JavaScript memory. In order to create an element, we need to provide a type and props. The type represents the type of DOM element. Props is an object where we define the properties of the element. One special property is called children. As the name suggests, it's the child or children of the element. It can be a text node, a primitive like a string or number, or an array of other elements. Now let's create a function that creates such elements. It accepts type, props, and children as arguments and returns an object with the mapped values according to the properties we discussed earlier. Since children can be strings, numbers, or other objects, we will handle this by iterating through the children. Now let's use JS6. To transpile JS6 into JavaScript, we use the following command. This takes the src folder as input and output the transpiled JavaScript files into the dist folder. Let's implement a straightforward function to render the page. We're recursively adding elements to the DOM. Here we check whether it's a text element or not. Then iterate through the element's properties and assign them to the actual DOM. We do the same thing for the children. Nothing special. As you can see, it works very well. But here is a catch. This function is synchronous. If you're familiar with the JavaScript event loop, you might know that there are synchronous tasks, microtasks, and callbacks. Callbacks are usually DOM events or set timeout calls. Microtasks are typically promises. The rest is synchronous code. Synchronous code has the highest priority. JavaScript will execute all synchronous code first. Only after that will it process microtasks and finally callbacks. This means that if we have a large tree, our main thread gets blocked. As a result, the page becomes unresponsive to user interactions. To fix this, we need to render the page without blocking the thread. This can be done by splitting the work into smaller units. So let's write a working loop that runs indefinitely. We are going to use request idle callback, which means the function will be executed when the browser is idle. This allows the browser to handle user interactions and other important activities without interruption. We continuously check whether there is any unit of work to do. If there is, we perform that unit of work. Note that the callback receives a deadline object as an argument. This object has a method called timeRemaining, which tells us how much time is left before the browser needs to exit the idle period. This helps us avoid doing too much work and blocking the main thread. Now it's time to introduce the fiber tree. The fiber tree is the structure we are going to use to render our page. One unit of work corresponds to one fiber. Let's say we want to render something like this. The fiber tree is organized in a way that makes it easy to find the next fiber to render. We have three main relationships in the fiber tree: parent, child, and sibling. Alright, now it's time to update our implementation. First, let's clear out everything from the render function. We're going to start fresh. Next, we will move the DOM creation logic into its own helper function. We will call it createDOM. This keeps our code cleaner and easier to manage. Now back in the render function, we set next unit of work to point to the root fiber. This is where our fiber tree begins. Then we move on to the real engine of our rendering process, perform unit of work. Here's what it does. First, it creates a DOM node from the current fiber and appends it to the DOM. Then, for each child of that fiber, we create a new fiber. If it's the first child, we set it as the fiber's child. If not, we link it as a sibling of previous one. Finally, we figure out what the next unit of work is. We try to go to the child first. If there is no child, we look for a sibling. And if there is no sibling either, we walk up the tree until we find an uncle. This is the sibling of parent. And just like that, we have got our perform unit of work function doing exactly what we need. But we got a problem here. we are appending a node to the DOM each time we work on element. Notice browser could interrupt rendering, so user could see incomplete UI while rendering, so it's not what we want. Because remember, the browser can interrupt our rendering at any point, so the user could end up seeing a half rendered UI. That's definitely not what we want, so we are going to fix that. First, we will remove the part of the code that directly mutates the DOM inside perform unit of work function. Instead, we will keep track of the root of the fiber tree separately. We will call it the work in progress root, or just whip root. Then, once we have finished all the work, and we know that because there is no next unit of work left, we will go ahead and commit the entire fiber tree to the DOM all at once. We will do that inside a function called commit root. This function will walk through the fiber tree and recursively append all the DOM nodes. That way, the user only sees the fully rendered UI and not a flickering half-finished mess. So far, we have only added elements to the DOM. But what about updating them? To do that, we need to compare the current tree to the previously committed tree to identify changes. This way, we can update only the parts that have changed. React calls this process reconciliation. To support this, we need to keep a reference to the current root. We will create a current root variable and assign it the value of whip root. Additionally, each fiber will need an alternate property to reference the previous committed tree. Let's now extract the logic responsible for creating fibers and move it into a function called reconcileChildren. This function will compare the old tree and the new tree. We will iterate over the children of the old fiber. To determine how to update, we compare the type. If the old fiber and the new element have the same type, we can reuse the existing DOM node and simply update its props. If the type is different and a new element exists, we need to create a new DOM node. Now let's update our commit work function. If the fiber has a placement effect tag, we do the same as before. Append the DOM node to the parent's fiber's DOM node. If the fiber has an update effect tag, we need to update the existing DOM node with the props that have changed. We can handle this in a separate function called updateDOM. In this function, we compare the props of the old fiber to the props of the new fiber. We remove any props that no longer exist and set any new or changed props. It's important to remember that there is a special type of prop we need to handle differently. It's event listeners. If a prop starts with on prefix, like on click, we treat it as an event listener. If the event handler has changed, we first remove the old one from the DOM node, and then we add the new event handler. The next thing is we need to add function components. So it means we could get not only an element but also function which returns that element. So we check if the fiber type is a function, and depending on that we go to different update functions. And in the update function component we run the function to get the children. What we need to change is the commit work function. Now that we have fibers without DOM nodes, we need to change one thing. We need to find the parent of a DOM node. So we will need to go up the fiber tree until we find a fiber with a DOM node. The last step is to implement state for our component using hooks. Let's start by creating a useState function. Before we call the function component, we need to initialize some global variables so that we can use them inside useState. First, we set the work in progress fiber and then we add a hooks array to it to support calling useState multiple times within the same component. We also track the current hook index. If a hook has already been created in a previous render, we retrieve its state. Otherwise, we initialize it. Then we add the hook to the fiber, increment the hook index and return the current state. We also need to provide a way to update the state. So we create a setState function. When it's called, it pushes the action into a queue we have attached to the hook. Then, just like we did in the render function, we set a new work in progress root as the next unit of work. This triggers a new render phase. At this point, we haven't applied the state updates yet. That happens during the next render. We retrieve all the action from previous hooks queue and apply them one by one to the hook's state. So when we return the state, it's up to date. Now let's test it with a classic example, a counter component. Each time we click it, the count increments by 1. And there it is, it works. We now have a fully functioning counter. Our proof of concept is working as expected. This video was inspired by Rodrigo Pombo's article, How to Write Your own React. I will drop a link in the description if you would like to dive deeper into the topic. That's it, thanks for watching, don't forget to subscribe and see you in the next one.